Lesson 3, Unit 1, Continuity and Behavior and Limits. By the end of this lesson, you should be able to use limits to determine the continuity of a function and apply the intermediate value theorem to continuous functions. You should be able to use limits to describe and behavior of functions. Starting today, we're going to learn about limits. Limits are going to be with us for the rest of the trimester, so we have to have a good grasp on them. Limits simply mean that we're going to approach some value c from the right and the left, and we're hopefully going to see what the y values are and hopefully see what this value is here. This is our symbol we use. The limit of f of x as x approaches c equals L. This is what your answers are going to be starting to look like. We have three types of discontinuity. We know what continuous means. It's just a straight continuous line. Discontinuous means there's a break in the graph. A function has infinite discontinuity at x equals c if the function increases or decreases indefinitely as x approaches c from the left and right. So this simply means that as I approach from the left, the graph gets higher and higher and higher. As I approach c from the right, it gets smaller and smaller and smaller. Infinitely higher and infinitely lower. Jump discontinuity. When we look at the graph, it looks like it jumped. That's exactly what you want to see. So this shows jump discontinuity. As we approach c from the right, it looks like it would be negative. As we approach c from the left, it looks like it's going to be positive. Removable discontinuity is it looks like we just took a small spot and just removed it from the graph. That's why it's called removable. One note, these two things are non-removable. These two are non-removable. This is removable. Continuity test. The continuity test states that there are three things that we have to do. First, we have to define f of x at c. So they're going to give us a value such as 2. We have to plug it in and see if there is a number. If there's a number, then it's continuous at that point. If there's no number, we know it's not continuous. Second thing we have to do if we're going to test for continuity, and we have to do all three of these, we have to make a table of values and approach 2 from the left and approach 2 from the right. If they approach the same value from the left and right, then that satisfies this second condition. The third condition is that this and this have to be the same. Well, now let's check an example so we can get a better clarification on this. So, we have this function. They want to know, is this continuous at the point 2? Use the continuity test. We have to use it for all three things. So starting here, I'm going to plug in 2. So I have to find f of 2. So I plug in 2. When I simplify this, it becomes 1. It's a solid number. It is continuous at that point. Now I have to make a table of values. So I'm going to make a table of values. And in the center, we're going to put 2, our x value of 2. Now, we're going to get closer and closer to 2 from the left and from the right. So we're going to start with 1.9. That's pretty close to 2, but we can get closer, 1.99. We can still get even closer, 1.999. And then on the other side, we're going to get closer the same way. 2.1 is pretty close, but 2.01 is even closer. And then 2.001 is closer yet. So we approach 2 from the right, we approach 2 from the left. Now we plug these values into this function here and get an answer. 0.52, 0.95, 0.995. So when I'm looking at this, as I got closer and closer to 2 from the right, I'm getting closer and closer to 1 in the y values. 0.52 is close to 1, 0.95 is closer, 0.995 is even closer. When I approach 2 from the left, my y values are getting closer and closer to 1 as well. So the question this right here says that as I approach it from the right, it gets closer to the same number as if I were approaching it to the left. This is what can satisfy this second condition. If it's satisfied, now we have to check that third condition. If I'm approaching it from the left and approaching it from the right, is it approaching this same number here? And the answer is yes. If that's the case, that satisfies the third condition. With all three conditions satisfied, we have just shown that this is a continuous function at 2. Now, let's check this one. We have this piecewise function, and we're going to see if this piecewise function is continuous at the point -3. When I plug in -3, well, I'd have to plug it in here. 2 minus -3, that's 5. So it does exist. So yes, this is continuous. So far, it's continuous at -3. So I plug in -3 here. Now, from this point, I'm going to choose some points that are closer and closer to -3 from both sides. -3.1, -3.01, -3.001, -2.999, -2.99, -2.9. And when I plug these values in, and as I approach -3 from the right, it looks like it's approaching 5. Well, that's good. That kind of matches up with what we had over here. But when I approach -3 from the left, it looks like it's approaching -11. These two are not approaching the same number from the left and the right. Therefore, this is discontinuous. Now, if you take a look, they're not approaching infinity or getting really, really big or really, really small. They're approaching a solid number. So therefore, this must be jump discontinuity. It's approaching 5 from the right, -11 from the left. That tells me this is jump discontinuity. So what does infinite discontinuity look like? Let's find out. So we have x plus 3 over x squared minus 9. Immediately, I can tell this is not going to be a continuous function. This function is discontinuous. And the reason I know that is because if I plug in -3 here, I've got 9 minus 9. Well, that's 0. Can't divide by 0. We know that's undefined. Therefore, this is discontinuous at -3. And if I plug in 3, same idea. It's discontinuous at 3. So at -3 and 3, it's discontinuous. So let's plug in -3 here and 3. And we're going to figure out what type of discontinuity this is. Again, we're going to choose values that are getting closer and closer to -3 on both sides. -3.1, -3.01, -3.001, -2.999, 9, -2.99, -2.9. So when I plug these values in, I've got -0.164, -0.166, negative 0.167, negative 0.167, negative 0.167, and negative 0.169. And we know this was undefined. Alright, so when I'm looking at this, I can see that I'm approaching the same number from the left and right. So even though it's discontinuous at negative 3, it looks like the value would, as we approach negative 3, would be negative 0.167. And if I were asking for what's the limit as x approaches negative 3, this is what you would write. You would put the limit of f of x as x approaches negative 3 equals negative 0.167. This would be your answer if I asked for the limit as x approaches negative 3. Now, let's check the other one. Again, we're going to choose values that are getting closer to 3. So, 2.99, 2.999, 2.999. Oops. Got too many 9s there. And then the same thing on the other side. 3.001, 3.01, 3.1. And when I plug these values in, we can see that as x gets closer to 3 from the right, the y value is getting smaller and smaller and smaller, and not by a little, but by a lot. It's shrinking really, really fast. So, and from the left, it's growing really, really fast. So we would say as x is getting closer and closer from the right, it looks like it's going to negative infinity. And as x is getting closer from the left, it looks like it's going to positive infinity. So if it's going to negative infinity, it's going to positive infinity. It's growing really small and then growing really large from one direction or the other direction. This is where we see that infinite discontinuity. And if we were going to write this, if I asked you for the limit as x approaches 3, you're going to put the limit of f of x as x approaches positive 3 equals, and then we have to decide from the left to right. So I'm going to say from the positive to start. So if I'm coming from the positive side, then it looks like it's approaching infinity. And then the limit of f of x as x approaches 3 from the negative side, or from the left, or from the right, then that equals negative infinity. This plus here means I'm moving toward it from the positive side. The minus means I'm moving toward it from the negative side. Alright, intermediate value theorem. This is the last thing I'm going to talk about before we call it good. The big idea here is this corollary, the location principle. If I know that f of a is negative, and then I know f of b is positive, then I know somewhere between them I had to cross the x-axis. That's an Algebra 2 concept, from if you guys remember it. So this is what it's asking. It's asking us to approximate the zeros. X cubed minus 4x plus 2. And then I'm going to plug in negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. The reason I chose those numbers is because from negative 4 to 4. So when I plug in negative 4 to this, I do get an answer. And the answer is negative 46. Negative 13. 2, 5, 2, negative 1, 2, 17, and 50. So as I plug these values in, each one of these x values into this, I get these y values. Now, what we're looking for is we're looking for where the y value goes from negative to positive or from positive to negative. So I'm looking carefully at this, and I see that it goes from negative to positive here, from positive to negative here, and from negative to positive there. So I see a sign change in my y values here, here, and here. That means that I have zeros. I have zeros between -3 and -2, 0 and 1, 1 and 2. My zeros are between -3 and -2, 0 and 1, 1 and 2. Now let's try this one. So again, I'm approximating the zeros between -3 and 3. So -3, -2, -1, 0, 1, 2, 3. Again, I plug these values in, and of course I'm giving you these answers because you guys should know how to plug these values in. So 6.16, 2.16, 0.16, 0.16, 2.16, 6.16, and 12.16. Now, I don't see any sign changes. But what I do see is these two numbers are really close to 0. I bet between -1 and 0, I bet it dips down and then comes back up between those two. And that's exactly what happens with this. If you were to graph this, you would see that between 0 and -1, this function comes down and then goes back up. So not only do I have one 0 between -1 and 0, I have two zeros between -1 and 0. And we would state that there are two zeros between -1 and 0. And that's where we're going to stop for today.